All right, in this one we're just kind of summing all the different types of distributions together. So we had our uniform and binomial distributions and hypergeometric distributions and whatnot. So I think two of them that kind of are difficult to separate sometimes is the binomial and hypergeometric distributions. So we're just going to take a look at those, the situation here that works out with the two. Compare them using a Venn diagram, and then compare them graphically as well using a histogram. So in the case we have here, we're drawing some names out of a hat. There's 5 male names, there's 6 female names. So we're going to use a Venn diagram to compare and contrast the probability distributions of selecting 4 names with replacement and counting the number of female names. So we're going to draw 4 names out of the hat, and we're going to count how many of them are female. And again, we're drawing a name, checking if it's a female, putting it back in the hat, drawing a name, checking if it's female, putting it back in the hat. We're doing that 4 times. And then in the second case, we're drawing 4 names without replacement and counting the number of female names. So draw a name, hold that name, draw another name, draw another name, draw another name. So we have all 4 names, and we can check how many of them are female. So if we want to compare the probability histograms, I have a little chart set up here. So I have a Venn diagram set up for us, and we're going to be comparing the binomial on this side, and then we'll do the hypergeometric on the other side. And so looking at these, binomial, the probability of the events in each case is going to be the same because we're putting the item back in. If we were talking about cards, we draw a card, we put it back in, we have the same likelihood of drawing another card, any of the other cards, where in the second case we're drawing one, then we're drawing another one, then we're drawing another one, and we're not replacing anything, so the probability is going to change because of the no replacement. So in the binomial, each situation is independent trial. So it's an independent trial. So one trial does not affect the other. And in the next case here with hypergeometric, because we're not replacing, it becomes dependent trials. The next trial, so when I pull one item out, the next item depends on the first item, and it can change it changes the probability because there's fewer items to choose from. In this case, names out of a hat. So when we're looking at binomial, a couple of the key portions of the formula is our probability of success, which is 6 out of 11, and then our number of trials, n, which is 4. So our probability of success is 6 out of 11. Our number of trials is 4. In the terms of the hypergeometric, things that don't quite match up, we have our n, which is our population size. So our n value would be our population size, which I should maybe write the actual population size in there, which is going to be 11, right? Our population size is 11. So we have 11 people in total, 5 males, 6 females. And then we have our value. So the R value is going to be 4. That's the number of trials that we have. And then the A value, which is the number of successful outcomes available. So there's 6 female names in the hat, so there's 6 successful outcomes available. R becomes our number of trials. And then we can plug those into their respective formulas. When we do plug them into their respective formulas and we create tables, I don't want to use another sheet of paper here because I'm trying to be quick about this one. So I'm going to just graph out, I've calculated them out already, and I'll graph out the probabilities here. So I'm going to use red for binomial, I'm going to use blue for hypogeometric, and I'm just going to put them each side by side. So the probability of 0 female names in terms of binomial is going to be about 4%. So we're looking at about right here. And then in terms of 1, we're looking at one female name, there's about a 20% chance. And then two female names, we're going to have a 37% chance. So that's going to be about here-ish. And then three female names is going to be at 30%. So about right there. And then 9% for the four names. And these are just roughly rounded. They're slightly different than this if you go to the full decimal. Okay, so there is our binomial. And now if we do side by side with the hypergeometric, then 0 is going to be 0.2. So it's going to be half of that first one. And then we have 18. So that's slightly lower than this one here. And then we get a greater chance, all the way up to 45% chance of drawing the 2 without replacement. That is a 2 down there. It's kind of not quite visible. My pen's not working very well. And then for 3, we get a 30% chance. So these are pretty similar. They're slightly different if I expand this number out here. This one's actually just slightly higher than 30. This one's just slightly lower than 30. When 30% when we work it out, it's 29.5 compared to 30.3. So this would be 30.3, this would be 20.5. So this is slightly higher, this is slightly lower. And then final one, we're looking at about 5-ish% chance of pulling the 4 female names. So there's our chart there approximately. That might be a little bit higher. But you see what happens in general is that our binomials, where we are drawing with replacement, we have a slightly higher chance of getting 0 or 1 and 4. But when we get to the middle terms there is a slightly higher chance with hypergeometric here with the 2 and 3 names pulled. And then it kind of has a slight bell shape in both cases, a little higher peak at 2 on the hypergeometric and a little more skewed to the right-hand side a little bit. So that's just a quick comparison of the two, and then we can refer, as we work through our problems, we'll see a few more examples of comparing the different types of distributions and looking at how they are calculated.